Welcome to Chapter 2 of our lecture video, and this is the chemistry unit. So we're going to talk about atoms and compounds, chemical bonds, looking at water, and then lastly the major molecules of life. So first off, we're going to talk about atoms. Atoms are the smallest units of an element. So when we talk about the elements in the periodic table like sodium and carbon and oxygen, those elements are made up of atoms. So the atoms are the smallest unit of an element. They are the units of matter that cannot be broken down into simpler substances by ordinary chemical means. So all matter is made up of atoms, and we're going to look at the structure of an atom. So if we look at the three particles that make up an individual atom, say of an element of sodium or helium, in this case we're looking at helium, there are protons and neutrons inside the nucleus of an atom, and the electrons are found around the outside in orbitals or energy shells, energy levels. And the electrons are what participate in bonding, so they can be shared among atoms depending on the type of atom, or they can leave the outer energy level of one atom and enter the outer energy level of another atom, as we see in ionic bonding. So if we look at the three particles, again we said protons and neutrons are found inside the nucleus, and electrons are found in orbitals or energy shells outside the nucleus, and they're constantly moving around outside that nucleus. And we know that protons have a positive charge, so they have a +1 charge, and electrons have a -1 charge. So these opposite charges attract one another, and that's what holds the atom together, is the attraction of the protons to the electrons. And neutrons have no charge, so they don't contribute to bonding, but they do contribute to mass because they have a mass of 1 atomic unit. So the proton has a mass of 1 atomic unit, the neutron has a mass of 1 atomic unit, and if I add those together, and there's only one of each of these particles, I would say the atomic mass of this atom would be 2, because it has 1 proton, 1 neutron. And then the electron is so tiny that it doesn't really have a measurable mass. It does have a mass, but it's such a small number that it really doesn't contribute to the overall mass of the atom. So if you think about, for example, if we look at the size of an atom as being the size of Lambeau Field, and you take a marble and put it at the center line, at the 40-yard line, that would be equivalent to the size of the nucleus compared to the rest of the atom. And if we look at the mass, most of the mass of that huge atom, like I said, using the analogy of Lambeau Field, that small marble at the center yard line would be the mass. Most of the mass of the atom is in that nucleus. So that nucleus is very powerful. Those protons and neutrons play a significant role in the mass of the atoms. But the electrons, like I said, are participating in the bonding behavior. So you look at an element. Elements are made up of atoms, and the elements are scattered throughout the periodic table here. We can see all the all the elements that exist that are known to science, and 92 of them occur in nature. So we can find 92 of these out in nature, and the rest have been discovered in the laboratory by splitting atoms and particles. But the 92 that we see out in nature are also shown here, and the most common ones in a human body are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Particularly carbon, hydrogen, and oxygen. Those are the three major atoms that we see that make up most of the molecules that make up the human body. So if you look at the atoms and the elements that they form, so these are the periodic table of the elements, they are arranged by their atomic number, and the atomic number is the number on top. For example, carbon has an atomic number of 6. That tells us that there are 6 protons in the nucleus, and there are 6 electrons that are spinning around on the outside of the nucleus. So the atomic number is equal to the number of protons and also the number of electrons in that atom. So the top number above each of these symbols is the atomic number. It tells us the protons and it tells us the electrons. It's the same number. So for example, if I look at hydrogen, the atomic number is 1. That means there's 1 proton in the nucleus, and there's one proton, or sorry, there's one electron spinning around on the outside of that nucleus. The atomic mass is the sum of the protons plus the number of neutrons. So for example, if we look at helium, helium has 2 protons, 2 electrons, but if I look at the mass, it has a mass of 4. So therefore it must also have 2 neutrons in that nucleus, because the mass is the number below the element, so that's the number 4 here. That's the protons plus the neutrons. So looking at the atomic number, which is the number above helium, it has 2 protons, but then it also must have 2 neutrons in order to come up with a mass of 4. Because remember, we said that electrons do not have a significant mass, so therefore they don't really contribute to the atomic mass of these atoms. So again, the atomic number tells us about the number of protons in that nucleus, as well as the number of electrons that are spinning around on the outside of the nucleus. If we look at the neutrons, they do play an important role in what we call isotopes. So these are atoms of an element that have a different number of neutrons. So therefore it's going to have a different mass. And how these isotopes are formed is by radioactive decay, which particles within the nucleus change the particle numbers, and we end up with these different masses as a result. And the radioactive decay that occurs is useful for use in medicine. So we use radioactive iodine for treating hyperthyroidism, and we use other radioactive isotopes when we're using them for imaging. When we look at radio imaging in hospitals, like a bone scan for example, they use radioactive isotopes to make pictures or images which are similar to like an MRI, but sometimes they give a little bit more definition, like in a bone scan. So, or for treating cancers, we also use radioactive isotopes in treating cancers. So these isotopes have uses in medicine, and they only differ by the number of neutrons. So it doesn't change the chemical activity of the atom in the sense that it still has the same number of electrons and protons, but the number of neutrons is what changes. And how that occurs is by radioactive decay, and we're not going to get into that topic here, but just be aware of what isotopes are and that it's the number of neutrons that is different among atoms that are isotopes. So we have carbon-12, carbon-13, and carbon-14. The small number here is the mass of those atoms. So they still have 6 protons, they still have 6 electrons, but their masses are different based on the number of neutrons they would have. So if we know that the nucleus contains the protons and neutrons, and we have a mass of 12, we know that carbon has an atomic number of 6, therefore it has 6 protons, and the number of neutrons that would add up to 12 would also be 6. So this one has 6 neutrons. This one would have 7 neutrons, because 6 protons plus 7 neutrons equals a mass of 13. And this would have to have 6 protons and 8 neutrons to add up to 14 for an atomic mass. So when atoms come together, they form bonds, depending on the reactivity of those atoms. So if 2 atoms come together, they may form a compound. And a compound is formed by atoms that share or give up or gain electrons. So some common compounds that you might be familiar with are the salts. And salts like sodium chloride is what we put on our food. And here we can see sodium is a solid, kind of soft metal, and it reacts explosively with water. And chlorine is a yellow gas, but if we combine sodium and chlorine gas in the environment, it simply forms table salt, and that's what we sprinkle on our food. So the reaction of these 2 atoms, the bonding of the atoms of these 2 elements, forms something very different. So the properties of that substance changes once a chemical bond forms. And the type of chemical bond between sodium and chlorine is an ionic bond, where one atom gains an electron and the other atom loses an electron. And we can see table salt is very different from the properties of the atoms that make up that compound. So if we look at, for example, hydrogen atoms, carbon atom, and an oxygen atom here, we can see that the electrons are found around the outside. So the first energy level outside the nucleus can hold up to 2 electrons, and everyone after that holds up to 8 electrons. So if an atom has an outer energy level of 8, it's considered stable and is not going to react. So if I look in the periodic table at the last column that starts with helium on the far right side, if we go back here, these all have outer energy levels that are full. Helium has 2 electrons in its outer energy level, and the first energy level of all atoms can only contain 2 electrons. So therefore that outer energy level is full, and this is a stable atom that will not react. If I look further down, for example, at the next one, neon has 2 electrons in the first energy level and 8 in the second for a total of 10 electrons. That would be full, because again, that outer energy level contains 8 electrons. So that's the maximum number of electrons that an atom can contain is 8 once we get beyond that first energy level. So here we can see this oxygen atom has 2 in the first energy level, and it has 6 in the outer energy level. So it's not quite full. It could handle 2 more. I could put one here, and I could put an electron here. So it would need 8 to be full. And the atomic number, if I look in the periodic table of oxygen, is 8, which tells me that I have, again, 8 protons and 8 electrons. So I can see the 8 protons in the nucleus. There's 2 electrons in the first energy level, and there's 6 in the next energy level, of which I could fit 2 more to make it full. But only if oxygen comes near another atom that has electrons to give up or share is it going to gain those electrons to fill that outer energy level. And it does indeed do that when it comes near hydrogen. One hydrogen atom will share its outer energy electron with oxygen, and so will another hydrogen atom share its outer energy electron. And that would give oxygen 8, and then bonds would form, covalent bonds, with 2 atoms of hydrogen bonded to 1 atom of oxygen. So again, looking at these bonds that form between atoms, if we have atoms coming together that form bonds, if they share electrons, that's considered a covalent bond. So covalent means to share. So anytime we have bonds between atoms that are hovering near one another and sharing their outer energy electrons, that's considered a covalent bond. Ionic bonds are transferring electrons from one atom to another. So sodium is giving up its 1 outer energy electron to chlorine, so chlorine has 8. That leaves the second energy level for sodium completely full with 8, and both atoms are content and full and stable, and a bond forms between them called an ionic bond. So covalent bonds share electrons, and ionic bonds give up or transfer electrons. And the bonds that are formed here are different in their strength. Covalent bonds are not quite as strong as ionic bonds. And there's a third type of bond that forms between water molecules, which are called hydrogen bonds, and those are the weakest of bonds, and they are easily broken between water molecules. So one nearby water molecule to another water molecule forms hydrogen bonds between the hydrogen atoms of one to the oxygen atom of another water molecule, and those are easily broken. And I'm going to show you a quick animation that demonstrates these 3 different types of bonds and how they form.